morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation, and we are continuing with our module 8, that is DER Integrated Distribution Network Fault Analysis and Protection. So, in the last class we have seen what is the impact of the DERs on the fault current levels or on the operation of the delays. So, today we will see how we can detect the fault currents. There are few classical and also the AI based methods. So, what are those methods? We will explore. So, first the fault in the power distribution network can cause obviously the equipment damage, supply disruption and safety hazards. So, but with the DERs the fault behavior changes that we have seen. So, what is that? The reduced fault current levels, asymmetry in the voltage and the current profiles, bidirectional fault current and non-sinusoidal waveforms with harmonics. That we have seen in the last class, that these are the causes or these are the effects of the DER installation with your fault current levels. So, what is the role of the detection and the classification algorithms, whatever we have designed or we are prone to design? Every fault detection enables selective isolation of the faulted sections, minimizing system wide outages and equipment damage. So, if you can do early fault detection, that when the fault just started, so within a few millisecond time, if you can detect that fault, so you can just isolate the portion, healthy portion from that fault, and then you can safeguard all those equipments which are inside that safe healthy portions. Otherwise, the fault will persist, then that will cause cascaded faults or cascaded effects in the network, and that will cause consecutive faulted section will increase, and your then healthy section will also collapse because of the faults. So, fault classification identifies the type of fault, LG, LL, double LG or 3-phase fault. So, if you have a good classification algorithm, that will say whether your fault is a phase to ground or line to line or double line to ground, or it is directly 3-phase to ground fault. So, if you can identify that, then and you have a 3-phase circuit, because your distribution networks are all 3-phase, and let us say you have fault only at the phase A. So, you can healthily operate your phase B, you can just turn off or segregate or isolate your phase A from the circuit. Otherwise, your B and C can send reduced amount of power to your load end. So, that is good. So, this identity classification is a needed thing. The system must determine the exact fault location and involved phases for faster recovery process. So, where is the fault actually, how much distance from the substation or from the node the fault had occurred. If the location is defined or identified properly, then the crew can directly go there and can repair the fault. So, that is also a identification, and also location identification is also highly needed. Accurate detection and classification ensures effective adaptive protection coordination under varying fault and network operating condition. So, determining that what is the classification and detecting the faulted condition, your coordination among the relays you can set up properly. Timely identification of fault characteristics supports real time grid self healing strategies and improves overall power system resilience. So, what are the methods normally used for classical fault identification method, which is normally used for the passive distribution network possible? So, threshold based approaches, first one. Second one is impedance based fault location. Third one is symmetrical component analysis. Fourth one is travelling wave techniques, and the last one is rule based techniques. So, generally these 5 techniques are used in the traditional passive distribution networks when you do not have DERs. So, what are those classical methods? For threshold base, the faults are detected on a signal exceeds predefined threshold. If it is an overcurrent relay, then you will see the current is more than threshold, then it will trip. If it is a impedance relay, then we will say that Z is less than threshold, then it will trip. So, this is the conventional threshold we set, and then we will see whether the actual value of that component, that impedance or the current, is lesser or greater. Depending upon that, we will take the decision. It is a simple and fast method suitable for real time monitoring. So, it is very fast, you just detect the current, You see that it is more than that and you just immediately you just trip off your circuit. Common thresholds include overcurrent, undervoltage or rated changes limit. So, depending upon that which relay you are operating. If it is an undervoltage relay, it will see what is the voltage, and the voltage if goes below the threshold, then it will trip. If it is a overvoltage relay, it will sense the voltage, and if it is more than the threshold, then it will trip. Similarly, for the overcurrent and the impedance relay. Easy to implement in both hardware and software systems, because you just need to fit only one threshold value and sense it and you are good. Threshold values are usually set based on the system studies or empirical data. So, you take the load current in place, you take the minimal fault current, and depending upon that you see what is the exact value you can set for your relay setting, that it will not trip for your loaded condition, but it will can sense your minimum load current fault current condition. But this is highly sensitive to threshold selection. First, that is the main problem. Poor tuning may cause false alarms or missed faults. So, the threshold selection is the primary key for this kind of an relays. That if your selection is not good and you set your threshold little bit lower, that sometimes if your system load goes load current goes up to that or maybe more than that, then your system will sense that and trip even at the highly loaded condition. Or if you say set your fault current limit to very high to avoid the loading condition, then what will happen if the minimum fault current is lower than that, then during the fault also it cannot recognize and it will not trip. So, you have to choose the threshold properly or wisely. Less effective under noisy conditions for detecting high resistance low impact faults. Okay? That means when it is a noisy environment, that means your fault current keeps on varying. So, at that time it cannot sense it, because sometimes it goes below threshold, sometimes it goes up to the threshold. So, that creates a nuisance, often used in conventional relays and protection schemes for initial fault identification, that is for the passive distribution network. That is ineffective for inverter based DERs where the current limiters are there. So, inverter based DERs, what it does, it restricts the fault current coming from inverters, but it cannot restrict the fault current which is coming from the contribution from the grid. If that is the case, then what will happen, that inverter is good, but your system will see that the relay will see the fault current from the main grid is less. So, it will not operate, but still the fault is there. So, if that is the problem, then at that time your this threshold based system will not be a good option. Then you have impedance based fault location, uses voltage and the current measurements to estimate fault impedance. So, you will see the before the fault, that means faulted section, before the faulted section what is the voltage, at the faulted section how much is the voltage, that is be close to 0 or maybe 0.1 per unit. So, if it is a dead short, then it is 0, if it is not dead short, if it is an fault resistance or fault impedance is involved, then it will be maybe 0.15 per unit or maybe 0.1 per unit depending upon the fault impedance value, and then you have I fault, and then you can calculate your impedance, line impedance. Fault location is calculated by comparing measured impedance with known line impedance per unit length. So, that is your impedance relay characteristics. Enables estimation of the fault distance from the measurement point. Fault classification is based on the phase involved and the impedance pattern. So, you will see different fault current combination LG, LLG, LL, what is the value of the Z, and depending upon that you will set your threshold for the impedance relay and you will check whether the impedance is becoming lesser than that or more than that. So, can be implemented using single ended or double ended measurement technique. So, you can either measure from both the side, then you take the voltage difference and then you can see that how much is the fault current and then you set the threshold. Otherwise, that you can take the data from either of the side. Okay. Let us say you take only from the healthy side, if you have a PT there, take that voltage, take the current and set the impedance. Okay. But for that, accurate line parameters and a fault type identification improve precision. So, if you have, because you are setting the Z, that Z includes what? Line impedance as well. Okay. So, if that accurate line parameters if you know, then only this setting will be perfect. Affected by factors like fault resistance, load flow and network configuration. So, depending upon how much fault resistance you have, if your fault is a dead short fault, then your fault resistance will be 0. Sometime we have a fault resistance of 5 ohm or 1 ohm or 2 ohm. Depending upon that, your total impedance value seen by the relay keeps on varying. So, that you have to know in your circuit, if a fault occurs, what will be the precise value of your fault current. Again, what is the network configuration? If you have a relay over here, okay, let us say you are giving supply there. So, for this path, the impedance is something else, and if the path is here is one switch and that path is going like this. So, for this path your impedance is something else. So, for these two conditions only you have to consider and your relay setting will be accordingly. So, then you have to know what is the system configuration. Widely used due to simplicity, speed and compatibility with the existing relays. DERs affect the voltage profile, that we have seen, that if you have a DER, the voltage profile will be not same as the voltage profile of your no DER condition. Then inverter output impedance not constant, always the inverter output impedance that keeps on varying depending upon the setting of the inverter. So, if that is the case, then your fault current relays seen, the impedance seen by the relay is not constant, and if that is not constant, then your threshold, whatever threshold you will fix, that threshold is not good enough to sense all the fault condition. Then symmetrical component analysis, which is a very famous technique we use for addressing any kind of unbalanced faults. What we do? We sense the unbalancing effect and then replace them with a component, sequence component, positive, negative and zero sequence component that we know already. So, it decomposes the unbalanced fault current voltages into positive, negative and zero sequence component. Symmetrical components help with identifying the type of the nature of the fault. Okay. How? The faults are detected by monitoring positive, negative and zero sequence component. So, if you have 0 and negative sequence component, that means the fault is a line to ground fault. If you have only negative sequence component, but no zero sequence component, then it is a line to line fault, because there is no ground involved. So, you will not get any zero sequence component. And if you see only positive sequence component is there, then you are sure that it is only a 3-phase fault. Okay. So, it can separate the faulted condition into symmetrical components, simplifying the fault identification process significantly. That is a very good and very traditional method. But the problem is, this method is highly effective in balanced network with strong conventional generation as the main source. So, if your system is previously balanced and the fault is creating the unbalancing effect, then this method is very good. But in our distribution network, we know that a network itself is an unbalanced system. So, if that is the case, so in the system you will see always positive, negative and zero sequence component are there. Okay. So, if all the 3 components are there, so at that time you cannot distinguish whether it is an unbalanced loading condition or it is unbalanced faulted condition. So, this method is good when your system is previously balanced and the fault makes it unbalanced. Accuracy reduces when multiple inverter based DERs cause system unbalance and distort symmetrical component measurements, just what we discussed now. Symmetrical analysis remains a standard approach for traditional grid, but less ideal for complex microgrids. Then you have travelling wave techniques. What is the travelling wave techniques? High frequency voltage and the current sensors are installed at one or both ends of the distribution line. These sensors are connected to high speed data acquisition units, typically operating in the megahertz range, that capture the transient waveforms generated immediately after a fault occurs. We know that the voltage and the current waves or current signals, normally we call it as electromagnetic waves. Those are electromagnetic waves traveling from your source to the end and then reflect back from again receiving end to the source end. Okay. Sometimes it reflect back, sometimes it transmit there. So, depending upon the value of that reflecting wave or the transmitting wave, we see whether it is a short circuit or open circuit, or what is the condition, how much is the impedance in the line. So, that properties are used for the travelling wave techniques, but for that you need a signal capture at both the side or maybe single side of the line in the megahertz range. Then time synchronization. To ensure accurate fault location, precise time synchronization is required. That means, both the side if you take the data, then that data, that clock of that sensors or that clock of that time measuring instruments has to be same. Then only you will get the system data at the same time from both the side. So, GPS clocks or precision time protocol systems are used to synchronize the sensors at different line ends, enabling accurate time stamping of the wave arrival. Then wave detection and pre-processing. Captured signals are processed using techniques such as band pass filtering or wavelet transforms. These methods isolate the high frequency components from the low frequency power signals and background noise, enabling accurate detection of the fault transients. Okay. Then you will do the time of arrival of the travelling wave, that you have to calculate. So, the time of arrival or travelling wave at each sensor location is calculated. In a two-ended system, the time difference arrival is determined. The step is critical for estimating the fault location by comparing the wave arrival time. So, all the time when a wave goes to the receiving end, then comes back, reflect back, then it is again coming, then it is again going back. So, if you can see at the fault point, if the current goes, then it will go to this point, then it will reflect back, then it will again go, then it will again reflect back. So, depending upon every time when it is coming back or reflected back at the measuring side. So, at that time we denote this time or we record this time, and depending upon that the fault location is estimated. So, using the known wave propagation speed and the TOA data, the distance to the fault from one or both terminals is computed. Mathematical models based on the line geometry and wave speed are used to determine the precise fault location, and this is the equation if you want to see the fault from the bus 1. So, what is that? If this is your total length L, then L plus that how much time it is taking to come back and go. So, L T11 minus T21. So, this two time difference you will see T11 you will see, T21 you will see, record this from the both the side, then take the difference between them. This is the speed of the wave, normally we consider it as the speed of the light, then divided by 2. Okay. If you do it, then you will get the location of the fault current. So, decision logic, after that getting the fault location, advanced logic and the algorithm analyze the wave characteristics such as amplitude, polarity, energy entropy, ground mode wavelet modulus maxima, and time profile to confirm the occurrence of a fault and determine its type. So, depending upon what is the amplitude, polarity, your energy entropy, or this ground mode wavelet modulus maxima, that will give you whether a fault is involving ground or not. So, depending upon that you can determine whether it is a phase to ground fault or phase to phase fault. This information helps in making fast and accurate protection decision. This is a very good method, but the problem is that you requires a high sampling rates, often in megahertz rates for range for accurate fault location detection. So, that is the main problem. You need a very high frequency data, and capturing that high frequency data needs your good equipment. So, that is a costly solution. Highly effective for transmission system, but difficult to apply in distribution networks with many DERs. High cost and infrastructure demands limit practical usage in decentralized and DER distribution grids. Okay. Then comes rule based classification. What is the rule based classification? Uses predefined logical rules and thresholds based on system behavior to classify the fault. So, you will say that if the current is this much, like it is same like a threshold value, but multiple thresholds you will fixed, and then you will give that level of the fault. What is a medium fault, or it is a very high level fault, or low level fault, or it is a loading operation. What is the condition that you will set depending upon the setting different if then rules. So, fault types are identified by if then conditions applied to features like current, voltage and phase angles. Simple to implement and does not require training data. So, that is a pre AI condition. That means you do not need a training data to simple the train your model. It is like a fuzzy logic where we set the membership functions depending upon their values. So, you set the values and depending upon that you will say what is the condition or what is the actual scenario we are incurring. Rules are typically derived from expert knowledge or protection standards. Suitable for systems with predictable and well understood fault signatures. So, that is only possible, that if then rule only you can set when you know the systems very well, that you know at which time or at which fault condition what is the voltage, what is the phase angle. If you know them correctly, then only you can set this if then rule properly. Limited adaptability, many struggle under noisy and the dynamic conditions. So, if your fault can keeps on changing because of the noise or the DRs, then that is your if then rule will violate and then it cannot sense the fault condition properly. Often used in conventional protection relays and early automation systems. Performance declines in nonlinear dynamic DER based grids with variable fault contributions. So, the overall limitation of the classical methods is that classical methods are computationally efficient, but poor adapt to the inverter based DER network complexities which we are facing today. Growing DER penetration drives the transition towards the intelligent AI based adaptive fault classification technique, which will AI, that is like you give the training data and how much is the diverse training data, depending upon that you will learn and it will act. So, it does not depend upon a if then rule or a classical method. AI can adapt any scenario and act accordingly. So, that is why these AI based adaptive fault detection techniques are now taking the space. So, why AI? Learns patterns from the data, current, voltage and the frequency, handles nonlinearity, noise and the system variability very easily, adaptive to changing network conditions, can classify fault types with higher accuracy. Training phase involves feeding labeled data to the model, testing phase applies it to the real time data. So, you can train the data easily and then just give the real time data and instantly it will give what is the where is the fault location, what is the fault classification, what types of faults you are seeing, everything it will give instantly to your automation system. Offers adaptive and intelligent decision making even under uncertain conditions. So, different AI based fault detection classification algorithm involves support vector machine, that is an ML based, that you will normally done by for binary and multi class classification with the help of kernels, maybe a radial basis function or for nonlinear cases, and as a feature normally we feed the RMS value, THD value and the voltage dip value. Then similarly decision trees and a random forest can be used with the help of your RMS and the duration of the fault, and that if you ensemble multiple decision trees together, then you will get a random forest and random forest classification method, and that will enhance your accuracy or system performance. But and it is good for only fault location classification. Then you can use k nearest neighbor method, which classifies based on the closest point feature that we know Euclidean distance, it will calculate and then cluster them together. Is a lazy learner and expensive during inference, sensitive to scaling. So, if you go for very large data, at that time clustering is a difficult process. Then you have multi-layer perceptron, that means artificial neural network, which is a fully connected neural network. You give the features like RMS, energy, harmonics and you will get the fault classifications. You can use even deep learning method where you need not to feed the features, you just give them the time domain waveform or frequency domain waveform, and then you will it will extract the features on its own with the help of the filters and classify the patterns depending upon your fault location. So, it will take the voltage and the current signal, raw signals, it will derive its own features and then give you the classification. Then you can use recurrent neural network or LSTM, which can capture the temporal dependencies. You can use the temporal dependencies, handle time series inputs very easily, and with the help of that it can distinguish the fault conditions. You can use few hybrid AI models as well, like you can take the out feature extraction. You can do the feature extraction with the help of cross wavelet transform or discrete wavelet transform, and then you take that wavelet transform features and then use them for the classification with the help of machine learning algorithm. That machine learning algorithm can be support vector machine or ANN or your random forest, anything. Or you can use combination of your deep learning as well, like CNN plus LSTM. You give the current and the voltage waveforms or the signatures to the this CNN plus LSTM, or like by merger of the deep learning algorithm. What the CNN will do, with the help of kernels, it will determine the features for the entire time series, but your LSTM will get the time series features. Then with these two features collated together with the help of fully connected layer, you can classify more efficiently. So, what are the features normally we used? That is with the signal processing tools. You can use the time domain features or you can use the frequency domain features. In the time domain features, normally we take the peak value, RMS value, rise time, decay time, or the from the extracted raw signals. Or you can use higher order statistical features like skewness, kurtosis, or any kind of other statistical features you can extract from a signal. And in the frequency domain, we use the fast Fourier transform to apply to convert the time signal into the frequency component and extract dominant frequency content. Similarly, we can see that total harmonic distortion and other useful features, frequency features we can get, that can be used for your protection or classification algorithm. So, time frequency domain also you can do the analysis, that is the wavelet transform you can use to provide simultaneous time and frequency resolution, making them ideal for capturing transient faults. Again, other techniques like empirical method decomposition, Stockwell transform, combine time frequency analysis and to extract the rich fault condition. After that, these are all the, if you use the machine learning, you have to only extract the features beforehand if you are using machine learning algorithms. But if you are using deep learning algorithm, then you need not to do that. The deep learning has the inherent capability that will extract the feature and do the classification. So, these are the features. If you are very specific about few features that you want in your system, even you can extract few features and then feed it to the deep and keep it, then you feed the raw signal also in the CNN. So, that will also extract few features, then merge all the features together and feed it to the fully connected layer for the classification. That is also good. So, if you are very specific about few features, at that time you can extract those features like time frequency, time series features or frequency domain features or time frequency domain features for your raw voltage and the current signals. But after getting all this huge amount of features what is extracted, you have to normalize them. So, feature normalization method like Z-score standardization and min-max scaling methods ensure balanced data input to the AI model. And then if your dimensionality is very high, because for a large amount of data you are collecting large amount of features. So, if that is the case, so you have to reduce, if you do not want to feed redundant amount of data to your AI tool, that may lead to sometime lower accuracy or sometime lead your AI tool to go mislead it for erroneous classification. So, if that is happening, so you want to reduce the data and keep only the dominant features. So, for that normally principal component analysis or linear discriminant analysis are very good, that will keep only the dominant features and extract out or filter out all the redundant information. So, for the dataset development and evaluation, you can fault detection models, you can create the datasets with the help of MATLAB Simulink or RTDS, that is a synthetic data collection, or you can use directly to the SCADA data or the PMU data. Simulated data provides control testing environments, while real world data adds the diversity and improve the model robustness. Then label all of them, like whatever data you received, you see for the training whether it is a line to ground or line to line or double line to ground fault. Then according to that, your AI model will be trained with this data. Then dealing with the imbalance, like because whenever you will collect the data, it is not the case you have collected 1000 data for single line to ground fault, and you will get 1000 data for double line fault. It may possible you will get 900 data or 800 data for double line fault, and for three phase fault you got 2000 data. So, there is an imbalance in the data. So, how you can cope up with this? So, that you can cope up by augmenting which data is less. You can add little bit of noise, let us say salt and pepper noise or Gaussian noise, you add with that signal and get the data augmentation and generate some synthetic data out of your original data, and then merge it with the original data set. That will enhance your data set requirement or make them in a balanced format. So, the metrics which we see for the classification is the accuracy, precision, F1 score that we normally derive. From the confusion matrix we see what is the per class, how much is the your true positive, false positive, true negative and true your false negative values that we can see, and from there we can determine this accuracy, precision and the recall. And we also see the receiver operating characteristic, that is the ROC, area under curve, is primarily used to measure binary classification quality and decision threshold performance. With this, we will see a case study of the fault classification and distribution networks, where the data is generated, then it is tenfold train and test. That means, whenever you will train a AI tool with only one shot training or one shot testing, you cannot specify or you cannot assure the accuracy level of that method. You have to do multiple time trainings and multiple time testing, and then take the average out of it, and then calculate the standard deviation. That will give you the actual accuracy level of your system. If your standard deviation is very low, it is close to 0, then your system is, your AI tool is robust. It is a very good. Or if it is its standard deviation very high, that means your accuracy level can vary widely. So, then it is not a very trustworthy AI tool. So, you split it, then use the trained data for the CNN, it is the CNN case study, and for the testing data use that for the CNN, get the predicted level and also the actual level, because for the testing also you will see whether the accuracy is, for testing the accuracy you have to know that which category it falls, and then use that and get the performance matrix computation. So, for that first you have to do the data collection. So, you can model this system, any system of the distribution network in the MATLAB Simulink or RTDS or OpenRT, you can format this network. Then the collected data by creating multiple faults in the distribution line by varying the fault resistance, fault inception angle, fault location, and also you can take the no fault data by varying the loads. So, with that you collect a huge amount of data set of different class levels, that means total 11 class levels having no fault, 3 single line to ground fault, 3 double line to ground fault, and 3 double line fault, then you have 3 double line to ground fault and 1 3 phase fault. With that, try to keep all the cases balanced, but if it is not, then also you can add the noise level and redundant data. These are the example of this, your double line to ground fault, this is your 3 phase fault, this is your the line to line fault, and this is your single phase to ground fault. So, you will get the current signatures and then fit that current signatures to a CNN model, having convolution layer, max pooling layer and different layers depending upon the depth you are deciding, and at last you flatten them and classify them with the help of softmax function. So, this is the output with the tenfold cross validation. If you can see with all the methods where you have to do the feature extraction. So, for the ML the major time go with the feature extraction and the training time is quite less. But for CNN the feature extraction time is nil, because it is inherently extracting the features, but the overall training time, because it takes the filter and the filter takes the features out, and then every layer max pooling, it takes some time. So, the total training time is more. But if you go to the testing, that is the more important thing, because training phase is mostly offline phase. We want the actual inherent automatic response at the testing phase, which is an online phase. So, depending upon that, the machine learning algorithms, if you see, they are mostly taking lesser time. This SVM, it is taking more time, your KNN, that is taking lesser time, even your decision tree is taking lesser time, but your CNN, that takes more time compared to your testing. Okay? And but their accuracy is also comparable. So, depending upon that what data set you are generating, which model you want to train, or which AI tools you are used, you can take multiple AI tools, compare them and see the best one, and that is your proper AI tool for that system. It may possible that which AI tool is good for one system, that is not good for other system. Okay. So, what is the practical implementation challenges? First thing is that model must process incoming signal and make fault decisions within strict time constraint to ensure reliable protection. You can see that your testing time is sometime it is one more than 1 second or 4 seconds. So, that you cannot spare if a fault is there. So, your fault location testing time should be as low as possible. So, your AI tool has to be precise, accurate enough as well, but has to be fast enough. Okay. So, depending upon that you have to choose. Then AI model is a black box model that you know. So, you cannot interpret how it is deciding. So, that is a challenge. Power grid configuration changes over time, requiring frequent retraining and updating of the AI models to maintain the performance. So, if one AI model is working good today, and if your power grid distribution network architecture or number of components or grid edge devices is increased tomorrow, so that AI tool may not perform good at that time. So, you have to always upgrade your training data to change the to keep the AI performance good. Then latency and computational limits. AI models must run with low latency. Hardware accelerators like FPGAs or edge AI based can meet this real time demands. Cybersecurity of AI models. AI based protection must be safeguarded against cyber attacks that could manipulate inputs, model or outputs, because you never know how it is taking the decisions. It is a black box model. So, it is very easy to manipulate that AI tool, because for classical methods you have a proper decision rule, you have a proper mathematics to derive to that solution. But for AI it is just taking the data, and by processing something it is giving you the outputs. You do not know what is that process. So, because of that it is very prone to the cyber threat. So, we have to keep the cyber security as well keep in mind. So, with this I will end today's lecture, and we will continue with our protection schemes in the next class. Thank you.